Right, so let's look at what Charles's law tells us regarding gases. So let's remind ourselves in terms of what do we need to model a gas. We of course need pressure, we need volume, we need temperature, and we need the amount of gas. Those are our things that we use to model our or any gas really, and specifically ideal gases that we are looking at in this theme. So Charles's law comes from the idea that you keep the pressure and the number of mole is kept constant or are kept constant. And if you keep that constant from PV equals nRT, you then will find that there must be some relationship between volume and temperature. So let's quickly just put volume and temperature on the same side. So that means volume divided by temperature is going to be equal to nR over P. And N and P we know are constant, and R is also a constant. So this means this relationship must be constant. Hence, the ratio between volume and temperature must remain constant. So that's what Charles's law tells us. It tells us that if we have a gas and we keep it at the same pressure and we have the same amount of gas, then the volume and the temperature will compensate in some ratio so that the gas or the pressure and the number of moles will remain constant. Okay. So if you want to change two things in the system, the others just need to remain constant. So it's looking at some of the examples, we have two situations. The first one is, or both of them are just relatively straightforward applications of this. There's only just one typo here. This just needs to be degrees Celsius. All right. So the first one says a certain gas occupies a volume of 35.5 liter at 0 degrees Celsius. Calculate the new volume at 63.78 degrees Celsius. Okay. So how can we use Charles's law to calculate that? It essentially tells us that we have some situation at the start where this gas remains at a constant pressure and the amount of gas remains the same. And hence we have that this pressure and amount of gas remains constant. Therefore, we can say that the volume in the first situation divided by the temperature in the first situation, so this is for A, must be equal to the volume after the change has happened divided by the temperature after the change has happened. And we want to know the new volume. So we want to solve for V2. So that implies then that V2 is equal to T2 V1 divided by T1. And let's just get our values here. So V1 is equal to 35.5 liter. Oh, that's V1. T1 is 0 degrees Celsius, and that's also known as 273.15 Kelvin. And T2 is 63.78 degrees Celsius, which is then equal to 336.93 Kelvin. So therefore, V2, if we plug in all those values, we see the Kelvins cancel, we're left remained with volume. It's going to be 43.8 liter. And it makes sense that let's look at this in a more visual way. So let's say we have a container, or a balloon is a better idea for this kind of thing. So we have a balloon, right? Sealed off balloon. The balloon is kept at the same pressure. So in other words, the pressure pressing down on it is the same, and the amount of gas in the balloon, so the number of moles, are not allowed to change. But we heat this balloon. So in other words, we add heat to it. So the little Bunsen burner that we have here, we give heat to the balloon, and it's at a volume and a specific temperature. But if we heat the balloon, what do we expect to happen? Well, we expect the temperature to increase, and that's what we see. But we also expect the volume to increase. But the volume will only increase if the pressure and the amount of moles stay the same. If the pressure were, for example, to decrease, then the volume would also remain constant. All right. But it's because we're keeping the pressure the same, the balloon will expand. And hence we have this situation that is called Charles's law. So then we have a new volume, a new temperature, but the pressure that's pressing down, or the pressure that the balloon is exerting, however you want to see it, and the amount of gas remains the same. So that's how you always need to remind yourself how these things work. PV equals nRT gives you a relationship between how the pressure and the volume scales to accompany the amount of gas with the temperature. So a certain amount of gas at a temperature will give you a certain amount of pressure that the gas exerts at a specific volume. You just look at the two sides of the equation. And then if you keep certain of them constant, then it gives you a ratio at which other things will change. Right. So B is another straightforward example of this application. It says a certain gas has a temperature of 153.32 degrees Celsius, not degrees Fahrenheit. We don't test that kind of conversion here. It says occupying a volume of 864 liter. Calculate the temperature when the volume is reduced to 10 times 10 to the power 9 nanoliter. Okay, so let's first start to get everything together. So we want to get, once again, V1 over T1 equals to V2 over T2. Our initial volume, a certain gas has a temperature, occupies a volume of 864 liter. At a temperature, T1 equals to 273 plus 153.2, so it's 273.15 plus 153.32, then should give us a value of 426.47 Kelvin. Right. So that's our initial situation. We want to know what temperature do we need to reduce this balloon to reduce the volume to 10 times 10 to the power 9 nanoliter. So 10 times 10 to the power 9 nanoliter. But you should see that 10.0 times 10 to the power 9 nanoliter is the same as writing it as this, liter. So it just cancels out. So it's just 10 liter. So we want to know by how much do we need to cool, or to what temperature must we cool this balloon to take it from 864 liter to only 10 liter. And again, that makes sense. If you keep the pressure constant, you keep the amount of gas constant, or there's no escaping the amount of gas, then the volume will decrease if we decrease the temperature. Right, the volume of the balloon will decrease if we decrease the temperature. So it's an unrealistic situation, but we'll see where we end up with. So again, in this case, we want to solve for T2. So in other words, T2 is equal to V2 T1 divided by V1. Yeah. Okay, V2 is then 10 liter, 10.0 liter, multiplied by T1, which is 426.47 Kelvin, and divided by 864 liter. And I mean, you can quickly see it's a 400 divided by 800 is about a half. So this rounded down is going to give us 3.94 Kelvin. So yeah, makes sense. We cool down the balloon, its volume will decrease from its initial volume. And we obey, well, Charles's law, not really a law, it's more an observation, seeing that if you keep the pressure and the number of gas molecules constant, then only the volume and the temperature will have a relationship with one another. We can recall from this equation here that volume will be proportional to the temperature. And that also makes sense. The higher the temperature, the higher the volume of your gas, and vice versa. And it leads to that V over T needs to be a constant ratio. Right. So this question isn't really supposed to be too daunting or too exciting. It's more just to convey the concept of what is so-called Charles's law, and what are the parameters that remain constant. And it's the pressure and the number of moles. Then you can relate the volume and the temperature. All right. Thank you for watching.